Thank you everyone for being here today. My name is Adrian Fernandez and I'm a PhD student in the group of permanent magnets and applications at IMDEA Nanoscience, Spain. And my talk is about nanocrystalline strontium ferrite material with enhanced permanent magnet properties. So this is the overview of my presentation. First, I will do an introduction and work motivation. Afterwards, I will discuss the experimental results obtained, and finally, I will finish with general conclusions of our work. So, first of all, what are permanent magnets for? So, permanent magnets here in our society can be found in different applications. For example, electronic devices, energy production applications such as wind turbines, or in the electromobility sector, the e-vehicles, for example. But the main issue or the main problem in these applications is that the energy requirement of these permanent magnets made that we need to use rare earth elements to increase these energy requirements, as I was telling you before. So as we need to use these materials and these critical materials, this arise some problems for our society. For example, the biggest problem is the supply risk of these critical precursor materials known as rare earths. And on the second hand, the environmental impact of the mining and refining of these materials. So Europe, trying to solve these problems, start to launch different European initiatives from a few years until now. For example, the Net Zero Industry Act, and lastly, last year, the Critical Raw Materials Act. So as this is a hot topic nowadays, our approach is to introduce a rare-free alternative known as strontium ferrite powders, a well-studied material that has really good properties, such as the abundant reserves and a good global distribution of the elements, and therefore the a low price in the market, good enough magnetic properties to can be used in different applications, and a low environmental impact in the mining and refining of these precursor materials, comparing with the rare earth-based permanent magnets. So our work is in the framework of the European Horizon 2020 passenger project, and the passenger project has these 4 goals. First of all, as my friend George said before in the previous talk, is the production of manganese aluminum powder at industrial scale. The second one is the large scale production of improved strontium ferrite powder. The third one is the industrial magnet fabrication using these improved powders of in the passenger project. And last but not least, the creation of 8 different pilot plants along Europe for material fabrication and the integration of these new rare-earth-free magnets in different applications, such as in the electromobility sector. So our approach in IMDEA Nanoscience is the use of our self-developed flash milling method for nanostructuring the strontium ferrite powders and increasing that way the permanent magnet properties. Afterwards, we use a recrystallization process via heat treatments to recover the ferromagnetic phase, known as strontium ferrite. Using this approach, we induce phase transformation in our system and the creation of defects and strain in the particles. So as you can see here in the same images, we start using a powder with an average size of 1 micron or so, and we end up in with powders that has tens of microns of particle size. So using our self-developed flash milling method, we managed to reduce effectively the particle size using just a few minutes of milling instead of using hours or days of the usual planetary milling. Along with this, we introduced or we managed to amorphize the surface of the particles. As you can see here in the XRD pattern, we start with a clear structure, a strontium ferrite structure, and as we increase the milling time, we amorphize the particle surface, and even we managed to transform the initial strontium ferrite phase into hematite phase, a more stable iron oxide phase. So to recover the ferromagnetic phase known as strontium hexaferrite, we apply a optimized recrystallization heat treatment, recovering that way the strontium hexaferrite phase. But we can see here that as we increase the milling time, we induce the formation of the hematite phase. So we can see now the improved magnetic properties of the strontium hexaferrite. As we increase the milling time, the formation of the hematite is induced, and we manage to increase the coercivity of this powder, the initial powder, almost twofold. So for here on out, we make a relation between the hematite formation and the increasing coercivity in this system. We further analyze this system using TM analysis. One of our partners in the Institute, Joseph Estefan of Slovenia, make this analysis and managed to found, even in the extremely mild 4 minutes plus a heat treatment afterwards sample, they managed to found large nanocrystalline particles with an average particle size of 7 nanometers. Thus meaning that we managed to retain the single domain size even after the heat treatment at really high temperatures for really long times. So for that, if we manage to do this relation between the formation of hematite and the increasing coercivity, we try to be sure that this relation is correct by adding a little bit of hematite prior to the flash milling process. So here you can see the comparison between, of the coercivity evolution as we increase the milling time for both experiments. In black, the one without the hematite content addition prior to the flash milling, and the other one with the addition of the hematite prior to the flash milling. So first of all, we can see that we reach the maximum coercivity point at lower milling times for the second experiment. And that we are achieving higher coercivity values for this case. So here we can see, and we can finally say that the hematite plays some role as a pinning center in our system, increasing coercivity of this improved powder. So further study made by our collaborators of the TU Darmstadt. They perform BSM measurements at different temperatures, and here you can see the coercivity behavior, the coercivity response of different samples. For example, here we can compare the starting powder with the milling, 25 minutes milling and 40 minutes milling. The starting powder presents the usual behavior, magnetic behavior of the strontium hexaferrite while we increase or decrease the temperature. And here we can see the main problem of using these ferrite powders in magnet fabrication for example, electromobility sector magnets. That is the risking of the demagnetization when we go to low temperature environments. So what we propose is that the increase in coercivity reached just by flash milling could be effective to avoid this risk of demagnetization in these low temperature environments. Here you can see, and even if as we go to the case of the addition of hematite content prior to the flash milling, just by milling 10 minutes, we can reach a more stable response of these powders. So here we are enhancing the thermal stability of these powders just by adding a little bit of hematite and flash milling afterwards. So now we'll go to the magnet fabrication. And here you can see that we are using the starting powder, the material as we has received from our partner collaborator, and the processed powder made by us just by flash milling 35 minutes and a recrystallization process afterwards. So this compaction, this magnet fabrication method is just the green compaction under the effect of magnetic field, and a sintering process at really high temperatures and long times to regain the mechanical properties of the magnet. So here you can see the full hysteresis loop, and here the second quadrant. We can see that we have an increase of almost 100 kiloohm per meter between the starting the magnet using the starting powder and the magnet using our post-process powder by flash milling 35 minutes and a recrystallization process. So we managed to improve the magnetic properties, and we managed to mostly preserve them during the sintering process. So last, I will be talking about the integration applications here in our project. And I'm proud to say that we already have some prototypes. Here, one of our partners, Vilo, have already made a rotor for a water pump motor. And here you can see the second prototype, that is a fully workable e-scooter. Here you can see the video. On the left is the scooter using ferrite in the motor, and on the right is a conventional scooter that you can find in the market nowadays using neodymium iron boron rare earth-based magnets. So they have similar behavior, the same efficiency in the motor, not in the energy, but maybe in a few months you can find this our e-scooter using only strontium hexaferrite in the market. So finally, to conclude our work, I can proudly say that we made the strontium hexaferrite powder with improved magnetic properties using our self-developed flash milling method and our recrystallization afterwards. We managed to mostly preserve the improved magnetic properties in our during our sintering processes of the strontium ferrite magnets. And last but not least, the integration into applications has already been started in our passenger project. So I want to thank my group of permanent magnets and applications at IMDEA Nanoscience, and thank you all for your attention.
Thank you, Adrian, for this very nice presentation. Congratulations. Do we have some questions? So maybe I will ask, Adrian, I saw that you were showing us the magnet at the end, no, comparing to the 1 cent coin, and then you show some application. So I see that there is no problem with the size, no? Like you can obtain actually bigger material. And how does it transfer to the series production, or how you see? Is it like it's always challenging, but how do you feel about that?
About the production of the magnets?
Yes, if we transfer it to some serious production or like more industrial production, right?
Yeah, of course. I can probably say that for the strontium ferrite powders inside of the passenger project, we are producing this improved ferrite in a scale of 4 tons per bag.
Oh.
So okay. It's already an upscale process. And right now the sintering process is being optimized. So right now it's only on the lab scale. But we hope that in a few months we can show you a few upscale results.
Perfect. Very nice. Congratulations.
Thank you very much.
Would be nice to see update in the future on that. Okay, I think we have no more questions, and it's time to close this session 7. Thank you very